everybody, welcome to iTTV. For today's lesson, we'll be looking at oxidation and reduction. We are actually continuing from the previous lesson whereby we defined a redox reaction using three parameters. The first one was in terms of gain and loss of oxygen. The second one was gain and loss of hydrogen. And the third parameter was gain and loss of electrons. So for today's lesson, we will focus on increase or decrease in oxidation number to define a redox reaction. So what is an oxidation number? To define a redox reaction in terms of changes in oxidation number is defined as an arbitrary charge assigned to an element. There are rules for assigning the oxidation numbers. Firstly, oxidation number of atoms and molecules in an element is 0. Example, elements zinc, helium, oxygen and chlorine gas, they all have oxidation number of 0. So it's important to remember certain rules for assigning oxidation number, whereby the first rule is that oxidation number for all atoms and for all molecules will have an oxidation number of 0, as was observed in the slide. The second rule is that oxidation number of hydrogen in a compound is +1. There is an exception because in hydrides, oxidation number of hydrogen is -1. So hydrogen compounds such as HCl and water would have oxidation number of hydrogen of +1. Whereas for sodium hydride, oxidation number of hydrogen is -1. So if you can look at the two examples given, HCl, because chlorine has an oxidation number of -1, it follows the charge of chloride ion. So therefore, the oxidation number of hydrogen will be +1 because the total oxidation number of this compound is 0. And then the second example given in the table was water, because there were 2 hydrogen atoms and oxygen has an oxidation number of usually -2. Therefore, oxidation number of hydrogen in water is +1. So there is an exception because we're saying that oxidation number of hydrogen is always +1 except for in hydrides, for example, sodium hydride. Because sodium has an oxidation number of +1, so hydrogen will naturally have an oxidation number of -1, so that the total oxidation number of the compound is 0. So that's a point to take note of. The third rule will be that the oxidation number of oxygen in a compound is -2. For the exception would be in peroxides. Oxidation number of oxygen is -1. Example, oxygen compounds such as sulfur dioxide and water, oxidation number of oxygen is -2, with the exception of hydrogen peroxide, whereby the oxidation number of oxygen is -1. So this slide is just trying to tell you all that usually oxidation number of oxygen is usually -2, but in chemistry there are always exceptions because oxidation number of oxygen in peroxides is usually -1 and not -2. Because as you can notice, in hydrogen peroxide, the hydrogen has an oxidation number of +1 because there are 2 hydrogen atoms there, so the oxidation number of hydrogen will be +2 and therefore the oxidation number of oxygen should be -1. To have a better understanding of this, let's jump to the board to illustrate this. So for hydrogen peroxide, we're interested to determine the oxidation number of oxygen. We know that hydrogen usually has an oxidation number of +1 except in hydrides. So we say let oxidation number of oxygen, say we put it as X and an unknown X. So if the oxidation number of hydrogen is usually +1, so it will be 2 times +1 plus 2 2x, because remember there are 2 atoms of oxygen here, so 2x. And usually, oxidation number of a compound is 0. Okay, so this will be plus 2 plus 2x is 0. And if we simplify it, plus 1 plus x is 0. Therefore, x, which is the oxidation number of oxygen in hydrogen peroxide, would be -1. So that's why the oxidation number of oxygen, which usually is -2, with the exception of a peroxide such as hydrogen peroxide, it is -1, as shown in the slide. So that's the exception for the oxidation number of oxygen. How about the fourth rule for assigning oxidation number? For monoatomic ions, the oxidation number of the element is the charge on the ion. For example, for the ion Fe2+, the oxidation number of Fe is +2. For Fe3+ ion, oxidation number of iron is +3. While for chloride ion, oxidation number of chlorine is -1. So this is quite a simple rule, and this only applies for monoatomic ions, whereby the oxidation number equals charge of the monoatomic ion. As you can see in the example, whatever the charge of the ion, that would be the oxidation number for the element involved. Next up, let's look at rule number 5. The sum of all the oxidation number of all the elements in a compound is 0. An example given is water, whereby 2 times +1. +1 refers to the oxidation number of hydrogen, plus -2. -2 refers to oxidation number of oxygen. Therefore, we find that oxidation number of the compound equals 0. Secondly, sodium oxide. There are 2 sodiums, so 2 times +1, because oxidation number of sodium is +1, plus -2, because oxygen usually has an oxidation number of -2, and we will work out that the oxidation number of this compound equals 0 again. So the point that you all have to remember is that the total sum of oxidation number of a compound will always be 0, as illustrated in the first example here, that the oxidation number for this compound is also equivalent to 0. So, and as you can see illustrated in the slides, we work it out that the oxidation number of compounds will always be 0 upon calculation of the individual oxidation number of the elements in the compound. So, let's look at the other rule, that the sum of all the oxidation number of all the elements in a polyatomic ion equals the charge on the ion. For example, OH-. Okay, so the oxidation number of oxygen, -2, plus oxidation number of hydrogen is +1. And we work out that the oxidation number of this polyatomic ion is -1. Then for CO3(2-) carbonate ion, because let's say if we are asked to find oxidation number of carbon in carbonate ion and we give it an X. So X refers to the oxidation number of carbon, and oxygen usually has oxidation number of -2, so we plus 3 because there are 3 oxygen atoms there, so plus 3 times -2, so it will be equivalent to -2. We want to test out that the sum of the oxidation number in this polyatomic ion equals the charge on the ion, and X would be equivalent to +4. So this further illustrates that the oxidation number of a polyatomic ion equals the charge on the ion. So that actually works out to one of the most important rules to assign oxidation number, that if the oxidation number of a compound is always 0, the oxidation number of a polyatomic ion equals the charge of the polyatomic ion, as shown in the examples given. Now, let's look at how to determine oxidation number of an element. So, remember, by actually applying the rules that were actually mentioned just now, that for nitrogen gas, oxidation number of nitrogen is 0 as illustrated in the first rule. For manganese ion, let's look to the board to see how to calculate the oxidation number of manganese. So we're interested to find out what is the oxidation number of manganese in this manganese ion. So even if you look at the slide, we actually designated oxidation number of manganese to be, say, X. X, it could be Y or ABC, depending on what alphabet you wish to use. So X plus, there are four oxygen atoms here, so plus 4, and usually the oxidation number of oxygen equals -2. And remember, we're applying the rule that the oxidation number of a polyatomic ion equals the charge on the ion. So this is -1. So we work this out to be X minus 8 is -1. So we carry forward to the right. X is -1 plus 8. So we find out that the oxidation number of manganese will be plus 7. As you can see in the slide, that is how it was worked out as well. But it would be clearer if I do at least one example on board. So let's look at the third example. That will be manganese dioxide. So let's say the oxidation number of manganese is also X. So we put X, and if you look at the slide, plus, because there are 2 oxygen atoms, plus 2 times -2 equals 0, because the oxidation number of a compound is equivalent to 0. So we work out that X equals plus 4. So the oxidation number of manganese in manganese dioxide equals plus 4. So let's look at other examples, such as sulfur dioxide, whereby we let the oxidation number of sulfur be X. So we write X plus, because there are 2 oxygen atoms, so 2 times -2 equals 0, and we work out that X is plus 4. So the oxidation number of sulfur in sulfur dioxide is plus 4. How about the next example, sulfate ion? SO4 2-, whereby we let the oxidation number of sulfur be X again. So we write X plus, this time there are 4 oxygen atoms, plus 4 times -2. Now this time we apply another rule that the oxidation number of a polyatomic ion equals charge of the ion, so equals -2. So we work out this little bit of algebra whereby X equals plus 6. So the oxidation number of sulfur for this ion is plus 6. Let's look at the last example, whereby we have Cl2O7 compound, whereby we let the oxidation number of chlorine be X. So there are 2 chlorine atoms there, so we write down 2X plus, because there are 7 oxygen atoms, so we put plus 7 times -2 equals 0. Remember, rule that oxidation number of compound equals 0. So we work that out, that X equals positive 7, and this shows that the oxidation number of chlorine will be plus 7 for that compound. So let's look at the first question. If, let's say, magnesium were to be reacted with sulfuric acid, and this produces magnesium sulfate as well as hydrogen gas, so would this reaction be considered a redox reaction? So think about it for a few seconds. Well, if you actually worked it out, you will realize that the equation given is truly a redox reaction, but we need to be able to explain how we have come to the conclusion. First of all, the reason is that there are substances which are being oxidized and being reduced, because a redox reaction means that there is reduction and oxidation taking place. So in order to truly understand this answer and reason, let's look to the board for this. Okay, so I'll draw another line. So to determine whether this reaction is redox or not, first of all, maybe I'll write the equation on board. Magnesium has reacted with sulfuric acid, and this produces a salt, which we know as magnesium sulfate, and this releases hydrogen gas. So what is the substance here that has been oxidized? So substance oxidized, I'll put the acronym here. This shows oxidized. So in this case here, do you think magnesium or sulfuric acid has been oxidized? Because if you notice, magnesium has actually experienced an increase in oxidation number, so therefore substance oxidized will be magnesium. And the reason for this, how do we know that magnesium has been oxidized? Because magnesium's oxidation number has increased. The oxidation number of magnesium has increased from... Now, what is the oxidation number of an element? Is always 0, 2. In this case here, the oxidation of magnesium is +2, because now it is an ion, magnesium ion, and we're applying the next rule that the oxidation number of an ion, of a monoatomic ion, equals the charge of the ion. So it's +2. So we know that the substance that has undergone oxidation will be magnesium. Now, how about the substance that has been reduced? What is the substance that has undergone reduction? Will be none other than the H+ ion. It's not sulfuric acid as a whole, but it's the ion itself. And the reason simply because for hydrogen ion, or we could say perhaps maybe we remove the bracket, because for hydrogen itself, oxidation number has, in this case, it has decreased from... For this case, the oxidation number of hydrogen here is +1, because it is an ion in this compound. It has actually decreased from +1 to 0, because the oxidation number of a compound is 0. So in this case here, you can notice that there is actually a substance oxidized and a substance that has been reduced, and therefore you can confirm that this is truly a redox reaction, because magnesium has been oxidized and hydrogen ion has been reduced. And to further illustrate this, there were changes in oxidation number. So if we look at the slide, what is the oxidizing agent here? Remember from previous lesson, the oxidizing agent is always a substance that is reduced. So the substance reduced here will be H+. Substance reduced is hydrogen ion. And how do we know that H+ ion is the oxidizing agent? Because hydrogen ion has been reduced. And remember, what is the reducing agent? It's the agent which has been oxidized. So in this case here, it's magnesium. The reason being because magnesium has been oxidized. So students always remember that to determine which is an oxidizing agent, it will be the substance that is being reduced, while the reducing agent is always the substance that has been oxidized. So Let's look at the second equation, whereby silver nitrate reacts with sodium chloride to produce silver chloride as well as sodium nitrate. So, do you think that this reaction is a redox reaction? If you think about it, this reaction is not a redox reaction. Reason being because there is no change in oxidation number for each element in the reactants after the reaction. So which means that this reaction, if you observe it carefully, the reactants and elements have no change in oxidation number before and after the reaction. So we conclude that that reaction was not a redox reaction. Next up, we look at metals that have more than one oxidation number. Let's start off with the IUPAC nomenclature. If an element in a compound has more than one oxidation number, then the Roman number is used to indicate its oxidation number in the compound. So this means that if an element usually has more than one oxidation number, we usually write down the Roman number to indicate the oxidation number of that element in the compound. Examples of metals with more than one oxidation state are usually transition elements such as copper, iron, chromium, manganese, and nickel, as well as other metals like lead and stannum. So, let's try to fill in the oxidation number and IUPAC names for the elements in the table below. Let's look at the first one, FeOH2. We're trying to find out what's the oxidation number of iron. And we find out that because OH is 2, therefore the oxidation number of iron for this compound is plus 2. And IUPAC name should be iron 2 hydroxide. Common name, ferrous hydroxide. Next up, FeOH3. The oxidation number of iron in this compound is plus 3, whereby the IUPAC name would be iron 3 hydroxide, common name ferric hydroxide. Third compound, PbO. Oxidation number of lead here will be plus 2. IUPAC name should be lead 2 oxide, common name lead monoxide. Now for the fourth example, we have PbO2. The oxidation number in this case here should be plus 4 because there are 2 oxygen atoms here. So 2 times negative 2 will be negative 4. So lead, Pb in this case here, should have an oxidation number of plus 4. So the IUPAC name for this lead oxide is known as lead 4 oxide. So with the fifth example in the table, KMnO4, let's look to the board to see how to calculate out the oxidation number of manganese for this compound. With that, I will draw a line here. So we have KMnO4, whereby we want to know what's the oxidation number of manganese here. So let oxidation number of manganese be X. So K usually has an oxidation number of plus 1. Potassium plus X, and there are 4 oxygen atoms here. Negative 2 equals 0 because oxidation number of a compound is usually 0. So this would work out to plus 1 plus X minus 8 equals 0. So X minus 7 equals 0. Therefore, X equals positive 7. So the oxidation number of manganese for this compound is positive 7. Then we look at another example, K2Cr2O7. This time, we want to find out what's oxidation number of chromium. So let oxidation number of chromium be X. So potassium, again, there are 2, and the oxidation number of potassium is plus 1. Plus, this time there are 2 chromium atoms, so we put 2 X plus 7. There are 7 oxygen atoms. Negative 2 equals 0. So this is plus 2 plus 2x minus 14 is 0. We simplify it, okay? So this will be plus 1 plus x minus 7 is 0. And therefore x minus 6 is 0. Therefore x equals plus 6. So the oxidation number for chromium in this compound is plus 6. Now with that, let us look at more examples that are listed in the table. So with the first example that was written on the board, KMnO4. So because the oxidation number of manganese for this compound is plus 7, so the IUPAC name will be potassium permanganate 7. Whereas for K2CrO4, the oxidation number in this case here will be plus 6, because we find out upon calculation that chromium's oxidation number will be plus 6. So the IUPAC name will be potassium chromate 6. While for the second example, which I wrote on the board for calculating out oxidation number, K2Cr2O7, the oxidation number of chromium in that compound is also plus 6. Therefore, IUPAC name will be potassium dichromate 6. And the common names are all listed in the table. Let's look at some more examples. MnO2. Oxidation number of manganese upon calculation will be plus 4. IUPAC name manganate 4 oxide. Whereas for zinc oxide, ZnO, oxidation number for zinc is plus 2. If you call it zinc 2 oxide, it's actually wrong. So we have to call it zinc oxide. Next example, H2SO4, oxidation number of sulfur is plus 6. So this is sulfuric 6 acid. Whereas the next example, H2SO3, oxidation number for sulfur is plus 4. IUPAC name will be sulfuric 4 acid, because oxidation number of sulfur is plus 4. NaNO3, sodium nitrate, oxidation number of nitrogen is plus 5. Therefore, IUPAC name is sodium nitrate 5. Last example, sodium nitrite, oxidation number of nitrogen is plus 3. So IUPAC name will be sodium nitrate 3. So let's have a short recap for today's lesson. We looked at the last and the fourth parameter to define a redox reaction, which would be changes in oxidation number, that either an element would experience an increase or decrease in oxidation number before and after a reaction. And secondly, we looked at how to determine oxidation number of elements. And thirdly, we looked at how to determine if a particular reaction given in your exam, whether is it a redox reaction or not, and students must be able to give their reasons why. And lastly, we looked at some IUPAC nomenclature based on calculating out the oxidation number of specific elements in compounds. So that ends the recap for today's lesson. So that's the end for today's lesson. Thank you so much for watching iTTV. We look forward to see you again the next time. Thank you and have a great day.